All right, we are now recording, but I think we're still having problems with Screencast-O-Matic and PowerPoint not talking with each other. Hopefully that's just going to be on this section. But before we get started while the projector's coming on the administrative calendar, today is the 23rd, and in case you hadn't heard, or if you know of anyone who needs to know this, yesterday was the 60% completion date for full-term classes for the Title IV funds. To me, that doesn't mean a lot except what I've sort of gathered, and I think this means any of the federal financial assistance. If you have not completed 60% of a term and you withdraw from the classes, you owe the money back. Now that 60% is passed, you don't. So if you know of anyone who is on federal financial aid and is hopelessly behind in a class, they can probably withdraw now and not have to pay the money back. That's only for full-term classes. If it was second mini-term classes, you have a while yet before you can do that, because we're just in the second week for them. All right, so that's that. Also, if any of you are on second mini-term classes and are on federal financial aid, your Pell disbursement is today. No, tomorrow. And that looks like most of what I see on the administrative calendar. Volleyball team, today's the 23rd, will be hosting Gadsden State Community College this evening on the Birmingham West Campus. That's Arthur Shores Fine Arts Building, which is also our gymnasium. That match starts at 6 o'clock. Okay, I will be on the East Campus until close to 7, so I probably will miss most of the match. Okay, but anyway, that's tonight, 6 o'clock. If you can get there, we have a fantastic volleyball team. Go watch them play. Now, this is something new. Came out today. It was sent yesterday, but I didn't receive it till today. It's from a woman who is a postdoctoral fellow at UAB and in a program called the Merit Scholars. She came across this one-week summer opportunity for college students interested in biopharma. Does that mean anything to y'all? Okay. Bio is, of course, living stuff, and that would be mostly people in biology-type majors. I don't know if y'all are bioengineering or anything like that, but they're interested in biopharma, and pharma means pharmaceuticals. So biopharma manufacturing careers. Now, if you're in math, you may still be interested in that. In any of the engineering, especially something like industrial engineering or some of the others, that might be. So something that would fit pretty well. So for these, this is a one-week summer opportunity for college students interested in biopharma manufacturing careers. And she said she thought some of our students might be interested in applying. Now, 1 week summer thing. The students are paid $1,000 and travel expenses are covered. Now, I don't know where they send you to. I'm assuming they're sending you to a pharmaceutical manufacturing plant somewhere. So for 1 week, you get paid $1,000 and they pay your travel expenses. The application deadline is sometime in January. I have a link you can go to if anyone's interested in pursuing that. Sounds like a pretty good deal, okay? It sounds like absolutely no cost to you that I can see, and you make $1,000 for a week. That's $52,000 a year if that were annualized. So that's not a bad starting salary. No, it's only for 1 week, but pretty impressive. All right, let's see if I can get my slideshow to go from current slide. We are recording, so that's good. All right, get a big blank screen here, and when I try to write, nothing will happen. Okay, so I still can't operate this, but hopefully this will be for this section only. So let's, nope. All right, so let's see if my red pen still writes. Any questions on anything we've covered so far? None? All right, we're on page 555, and it's example 4, repeated quadratic factors. It says find this integral. No wonder this has kept its ink. The top is really tight. The integral of 8x cubed plus 13x over x squared plus 2 squared. Dx. All right. Anyone want to suggest a procedure to follow? Second? I can't. Factor the numerator, we certainly could do that. Is that going to help us any though? We can factor out an x, and that would leave us 8x squared plus 13. And that's not factorable. And usually it's the denominator. We like to factor the numerator if we can, if it helps to eliminate anything in the denominator. For instance, if it had an x squared plus 2 left over up here, yes, okay, that'd be really good because you could cancel one of those out. It doesn't. So, yeah, you can factor that, but it really won't do you any good. And it's not a bad thing to do, to try, but it won't produce much because all you'll get is an x on the outside here, not outside here, but x here, and then 8x squared plus 13. Not going to help you here. Okay. What next? Well, anyone want to give U substitution a try? I think that would be pretty useless because if you did expand this denominator, that would be x to the 4th plus 4x squared plus 4, if you squared that, okay? And 8x to the 4th, no, I'm sorry, x to the 4th, when you try to do the dx for that, if you let that be your u, then the du for that would be 4x cubed, which you might be able to do something with that, but then your next term would be 4x squared, and that would give you 8x. You got a 13x there. No. U substitution won't do you any good either. Okay? What else? Now, I know someone wants to try a trig substitution, don't you? Please say no. Okay. You can do it through a trig substitution, and again, your x would then be square root of 2 times the tangent of theta. That would be what your x would be, and you can proceed with that, and I can't even imagine what that numerator would turn out being. Ugh! Awful. Okay. So let's not do that. Okay? What else? It's the title of the section. Partial fractions. Why don't we try that? Okay? So let's take this and fiddle with it for a while. Okay? That'll be 8x cubed plus 13x over, we'll leave it written just like this, x squared plus 2 squared. Okay. Now, anyone think you might be able to factor this any further? Not the end part, but you can split that up as x squared plus 2 times x squared plus 2. It is a multiple factor. Okay, so what do we do with multiple factors? When you have one raised to a power. Anyone recall?
AX plus B.
Okay.
CX.
The numerator here would be ax plus b, and the reason for that, this is a irreducible quadratic factor. So its numerator needs to be a linear term. Okay? What would that be over?
X squared plus 2.
X squared plus 2. Okay, we don't need that parentheses then. Then what?
CX plus D.
Okay. Cx plus d, is that what you said? Doesn't matter what you name those. Plus d. And that would be over what? X squared plus 2 squared. If it was just over x squared plus 2, then you could just add these together. You'd have a plus cx plus b plus d. That wouldn't give you anything. But yeah, you have that. You have to include every factor that's here up to that number of times. Okay? So we just got 2. Now, what would you do next?
Multiply both sides.
By the common denominator. So we'll put this in parentheses, multiply it by x squared plus 2 squared. We'll multiply this one, put it in parentheses, by x squared plus 2 times x squared plus 2. I'm writing it that way for a reason. I don't have to, but I chose to. And this one we'll multiply by x squared plus 2 squared. Okay? And you'll notice here, this goes out very nicely. One of these goes out, leaving you one, and both of these go out. Okay? Now, what does that leave you with? Your numerator here is still 8x cubed plus 13x. Okay? In fact, that's all you got here. That's equal to what? Okay, ax plus b times the one factor here. You want to go on and FOIL that so we can see what that turns out being? Please say yes. We love to do that. Okay? So let's FOIL this. What would that give you?
AX cubed.
Ax cubed. Let's do this, yeah, plus bx squared. Then we'll do this one.
2AX.
Plus 2ax. And finally,
2B.
plus 2b, or not 2b. Okay. Got it. Now, the last term, all we have is a plus cx plus d. All right. We have one equation here, but it has 4 unknown variables. Now, x is no longer the variable of interest. It's these coefficients, a, b, c, and d. So we're going to work on getting those. So let's look at all the x cubed terms. We have one on this side and one on this side. What does that tell you? If that's got to be equal, that says a is equal to 8. Oh, that's pretty easy. Done. Okay. Now, how about the x squared terms? What does that tell you?
B is 0.
B is 0. Ha! That's not too bad. Okay? B is equal to 0. Because you have no square terms here, only have one there, so that means B has to be 0. This is going faster than I thought it would. Now what? Linear terms. Okay? On the linear term, on this side you've got 13, and on this side you've got 2a, but a is 8, so that would be 16, right? This is the coefficients for your x, plus c. You see that? You're dealing with the coefficients for your linear x term. 13 on this side, and you got 2a plus c on this side. But we already know what 2a is. A is 8, so 2a is 16 plus c. The only x is over here. Okay? What does that tell us? Anything? C is equal to what? Negative 3. You got it. All right. Now we deal with our constant terms. Once we get Fred here. Okay. We're doing the example 4 on page 555. This section, remember, the PowerPoint seems to be corrupted, and so we can't do anything with it. So I'm having to write on the board, trying to talk loudly enough so people at home can follow this, which I'm sure they're doing, okay, or will be doing. So C is equal to negative 3. All right, next.
Is D just 0?
Okay, the constant term tells you that this is 0 is equal to, now what constants do we have here? That has a 2b, which that is already 0, so that is D, so D is also equal to 0. Boy, this came out a lot easier than I thought it would. Usually at this point you could have up to 4 equations, 4 unknowns. You have to do a matrix or something like that to solve it. And probably those are somewhat unfamiliar to you, so this is what we've got. Now, this is sort of scratch work, so I'm going to erase this, but I want to hang on to these 4. Okay? Now, let's go back here, remembering our first setup up here. This thing right here, which is our integral, was ax plus b over this plus cx plus d over that. So let's do that to our integral here. Okay? A is 8, so it'll be 8x plus b, which is 0, over x squared plus 2, x squared plus 2, okay? I'm going to put a dx there, plus, I may not need to, but I'm going to. But I think I'll change that to a minus here, because that's going to be a minus 3. I probably could have pulled the 8 out, but we'll deal with that later. C was minus 3, and this is going to be minus 3 times the integral of x, because the d is also 0, x dx over x squared plus 2 squared. That's what this has broken down to using these coefficients. How would you proceed now? Does everybody see how that produces this? Any questions on that part? Okay.
So basically, we just went back to the
Yeah, because this thing here, this was what the integral was here is equal to ax plus b over this part plus cx plus d over that part.
And we just plugged in all the
Plug in these values that we got here.
Okay.
8 for the a, 0 for the b, minus 3 for the c, and 0 for the d.
Okay.
And then rewrote the integral like that. So, is that solvable? done, in effect, is gotten things back down on a basically far lower degrees of your polynomials.
Isn't that 8 natural log of x squared plus 2?
Okay? How did you get that quickly?
Well, that's the, when you take the integral and the x's in the denominator, it's natural
Okay.
log.
All right. So you pulled the 8 out. Is that right?
Yeah.
Okay. But then your derivative of the denominator is (2x), right?
Oh, okay.
Yeah. So you'd only need to pull a 4 out. Now, if you can do it that way and see it and not make mistakes with it, fine. But what would be our standby for doing something like that? U substitution. What would that be?
Let u equal x squared plus 2.
X squared plus 2. Okay, then what's the next line? Always du is equal to 2x dx. Okay, and we have an 8x dx. So let's pull a 4 out of this, and this would then be 4 times the integral, because you pull a 4 out, and that leaves you a 2x dx, okay? And that would be here, so that's your du up here. That's ugly, isn't it? And then what do you have down here? Just u. And you're absolutely right, that does come out being a natural log of that. So you have 4 times the natural log, but let's go and plug in what u is, or u are. That's x squared plus 2. And I don't need absolute value bars. Why? Yes, x squared is always positive. You add 2, or could be 0, but you add 2 to it, it's always positive. Okay? So that's the first one. How about the second? What are we going to do with that? Second? Yes, I think a u substitution would be in order here too. And guess what that u substitution will be? That u equal, same thing, x squared plus 2. Then, this part's the same. Du is equal to 2x dx. Okay, we don't have a 2x dx. We only have an x dx. You can't bring a 2 back. Well, you could. Make a 3/2 out here, and yeah. But what I was going to do is just divide by 2 and make that do it, and that's going to put our denominator there. So what do we have then? Minus 3/2, because you divided by 2 here. The
du over u squared.
This would be du over u squared, which I really don't like writing it that way.
So u to the negative 1 du.
Okay, you're going on integrating it? Is that what you're doing now?
No, I was rewriting it.
Rewriting it? Well, then that would be to the minus 2. Wouldn't
Yeah,
it?
minus 2.
Okay, yeah. Okay, so that would be minus 3/2. That's ugly 3. The integral of u to the minus 2 du. What does that integrate as? Help me, somebody. Pretty good old power rule, isn't it? This is where the similarities end. You have the same u substitution, but because you have a different denominator here, you have a different integration. So what does that give? How do you antiderivative of u to the minus 2? Oh, yeah, I see you. I thought that was dx for a moment. Okay. How do you do a power?
Add 1 to it.
Add 1 to it. So this would be u, add 1 to a minus 2, and what do you get?
Minus 1.
Minus 1. But then you divided by -1, which is the same as multiplying by -1, which will then knock out your minus sign, right? Okay? So that gives you 3/2 u to the -1, or 3/2 over u. And one other little thing. Plus c. Okay. Because this is indefinite interval. But now, we can go back and substitute what your u is, or u are. So this will be plus 3/2, and what is u? X squared plus 2. So this would be 3/2 of 1 over x squared plus 2 plus c. All right. Now, I don't know if that's how they leave it or write it. They could put 3 up here and double that down there. I don't know. But you could actually change this to the log of x squared plus 2 to the 4th power if you wanted to. That's fine too. Nothing wrong with that. This is an acceptable answer. And how do they leave it? 4 log x squared plus 2, very good for them, plus, and they put the 3 over, and then put 2 on the outside, x squared plus 2, plus c. All right. Now, interestingly, they drew the graph of this function here, that thing that was inside the radical, and then they also did the graph of your 8x over this, put minus 3 x over that, and graph the two of them in the same viewing window, and they do line up on the same graphs. So you can do that as a check if you have a graphing calculator. That doesn't help you solve the problem, but it does show that you did your math right. Now, what I found interesting about this graph, and this is something good to store for further use maybe. If I were to just have given you that function there, this y1 is equal to 8x cubed plus 13x over x squared plus 2 squared, and I would have asked you what kind of function that was, what would you have told me? Certainly that numerator is an notice the exponents. 3 and 1. Both odd numbers. That is an odd number. The denominator certainly is even. Even if you expand that, that would be even. So my tendency would have been said, this is going to be an even. But it isn't. It is, look at that graph. What's that the graph of? An odd function. So that numerator, the denominator doesn't contribute anything to the even and oddness of it. It's sort of like odd divided by even is still odd, okay? Kind of like minus divided by plus is still minus, okay? You might store that away for future use or investigation to see if that always worked, but it certainly is an interesting little aspect, which you probably don't even care about. But I like thinking of stupid things like that. Okay. Now, I've got to erase my board because I can't just wipe out the screen like I'm used to doing. Anyone need any of this left a little longer? Everybody okay with it? You got the 4 down? Yay? Okay. There it goes. Goodness, my shoulder hurts. My left shoulder, and I'm left-handed. Getting old can be a terrible thing, but it beats the alternative, which is dying young. So don't brag about it too much. sometimes hurts. Okay. Top of page 556. When integrating rational expressions, keep in mind that for improper expressions, you have to do something first. What if this had been an integrand? Your n of x over d of x, that's numerator is a function of x, polynomial function of x over denominator polynomial function of x. What is this? Is 2x cubed plus x squared minus 7x plus 7 divided by x squared plus x minus 2. Okay? What you think about that? What would have been your procedure for that if that would have been your integrand? What would go through your mind?
See if there's any like terms I can cancel out.
Okay, well, first you would say Dawson's here. And then once you got over that shock, that thrill or whatever, what would you say?
Like factor in the numerator and denominator.
Okay, that would be my first gut reaction to it. See if we can factor that numerator, especially that denominator, because that sure looks factorable to me. Numerator, though, is a 4-term polynomial. Only way I know how to factor that is grouping, okay? And if you try to group this one, you get a factor of x squared, and you have a 2x plus 1, all right? And grouping this one, factor out a minus 7, and you get an x minus 1. But at that point, you have no common factors to proceed. So, good try, but it's not going to produce anything. But how about that denominator? Does that factor? How?
X plus 1, x minus 1.
Not quite. I'll buy the x minus 1.
Oh, plus 2.
Plus 2. Doesn't that factor well? Yay or nay? Right? Now, since that factors, your 0 for this one would be a minus 2 or a 1. So I want to see if minus 2 or 1 is also a 0 for this one. If so, we can factor it. Okay? So let's see. Let's put in a minus 2 here. That would be a
Minus 8.
negative 8 times 2 is
Negative 16.
negative 16
Plus 4.
plus 4, so that'd be a negative 12 plus 14. It's getting completely out of hand. Nope. X plus 2 is not a factor of that. That's almost a dead giveaway because how could you wind up with a 7 here if 2 is there? So, no, we're convinced that. But perhaps 1. Will 1 work? Let's just plug in x equal 1 here. What do you get? 2 is 2 plus 1 is 3 plus 7 is 10. Nope, that's not going to work either. So the idea of factoring, a great idea. Always try it first. But if it fails, you maybe lost some time, but it's still worth the effort. If you have found some common factors there, get rid of them. Okay. But unfortunately, this one didn't happen. So when that fails, and guess what? This stuff is sometimes trial and error. Okay? No error is made, but try it. Try to see if you can simplify. Save yourself grief later. This one, unfortunately, you can't. So that one's scratched off. You can't factor the denominator. Don't know of any way to factor the numerator. Certainly, neither of those factors will work in the numerator, so hang it up, Jack. Okay? What next? You just go on and integrate this thing? Say again? Divide. You're absolutely right, because you cannot do partial fraction decomposition if your numerator is greater degree than your denominator. In other words, if it's an improper rational expression. So, how do we divide? That's another bag of worms, isn't it? So I'm just going to bring down my division here and put this inside here. 2x cubed plus x squared minus 7x plus 7. Okay? Time out. Okay? Warning. Before you do log division of polynomials, be sure that both the divisor and the dividend are in decreasing orders of your power. 2, 1, 0, that's fine. 3, 2, 1, 0, that's fine. And there's no missing terms. And I just verified there's no missing terms. If there was a missing term, guess what you got to do? Insert a 0 for that term. Okay? So, now that we're set up and convinced we can do this, how do we proceed? Remember how to do long division with numbers? You people who have grown up with calculators and never had to do one in your life, maybe? Or you avoid them like the plague? You remember how to do long division? You do left to right. Everything else, addition, subtraction, multiplication, you do right to left. Division, you do left to right. So let's do the same. Start with the first term here, x squared into 2x cubed. How many times will that go? 2x times. I think the book probably puts this over here. I like to do it there. That's the one I'm working with. It doesn't matter where you put it. Okay? Then what do you do next? Multiply. 2x times x squared is 2x cubed. That's good. Then 2x times x is plus 2x squared. And then 2x times minus 2 is minus 4x. Okay? What do we do next in long division? Subtract. But now that we've got signed numbers here, I suggest change signs and add. So I'm going to make that a minus, this a minus, and that a plus, and add them. That, of course, adds a 0, which is exactly what we wanted it to do. What does this give us? Negative x squared. Negative 3x. And bring down the plus 7. Do it again. This time we do x squared into my, how do you know that you continue? If the degree of the divisor is equal to or greater than, equal to or less than degree of the remainder, you keep working. If this was lower degree than that, you're done. But this is the same, so you keep working. So x squared into minus x squared will go minus 1 time. Then you multiply. Minus 1 times x squared is minus x squared. That's exactly what we wanted it to be. Minus 1 times of x is minus x. And minus 1 times minus 2 is plus 2. Okay? And then you can either subtract. This one's not, it's not hard to subtract this one. But I still like to change signs and add. Okay? And what does that give us? Those go out, which is exactly what they're supposed to do. What does this give you? Negative 2x plus 5. That's now your remainder because this degree is less than that degree. Okay? So how we write this is, there's a couple ways you can write it. I sort of like doing it this way. Minus a 2x minus 5. I'll pull the minus sign out. You don't have to. You can put a plus here and then put this exactly like it's written. over x squared plus x minus 2. Okay. Now, if indeed this had been your integrand, that's how we were assuming, now you're integrating this. Well, I can integrate that, right? What would that integrate as? Come on. If that was in the integral, what would be the antiderivative of 2x? X squared minus x. There's your first part done for you. Okay? Much easier. Okay? Now your partial fractions you do with this part. And since we already know that factors x plus 2 times x minus y, we can proceed to separate this out and do our integration by parts. Partial fractions that way. Okay? They didn't work it out. Do you have a particular hankering to work it out or not? It's up to you. Work it? Okay. So, if this had been your integral, and you had a dx here, now it would have been, can I go and just write out what that is, or should I write it as an integral? Up to you.
Let's just make it what it is.
Okay, so that would be x squared minus x minus, now I like the minus here, they put it on the inside. I don't care which way you do it, just keep up with it. Be sure you change that one if you put it on the outside. The integral of 2x minus 5 over, can I go on and factor that? Remember it? I had it right there. What was it? X plus 2, x minus 1, dx. Okay. This goes back to easy ones, doesn't it? Okay. Here's your x squared minus x. Don't forget that. That's important. Minus. Okay, what happens here? Let's go over here and do our work. Your 2x minus 5 over x plus 2 times x minus 1. What would you put on the right-hand side? Anybody?
Ax plus b.
A over what?
X plus 2.
X plus 2. Remember, if this is a linear factor, this is a constant up here. Okay? Plus b over x minus 1. Now what do we do next?
Multiply by the common denominator.
Yeah, multiply by that big old denominator there. So this will be this thing times x plus 2 times x minus 1. That doesn't really matter because they're both going to go out. This will be times x plus 2 times x minus 1. And this will be times x plus 2 times x minus 1. Okay, when you do this, these go out, leaving you just 2x minus 5. Over here, what happens?
The x plus 2's go out.
The x plus 2 goes out, they've been dating, okay? And this is a times x minus 1. Plus b times x plus 2, because of x minus 1 divided by. And what's your next step? It's so long since we did it easily. Have you remembered it? Oh, come on. It seems like cheating, but you get away with it.
You have to solve for one of the a's or b's by
Okay, how do we do that?
0. So like let x equal
Let x equal what?
1.
Yeah, that's going to be good. What does the left-hand side become then?
-3.
-3, right? Is equal to, what does that become?
0.
0. What does this become?
3B.
3b, right? See that? When x equal 1, this becomes -3. That becomes a 0. This becomes a 3 times b. And what does that imply? B is equal to -1. Okay? Oh, that works so well. What else might we try? Let x equal -2. And what does the left-hand side become then? -9 is equal to, what does the right-hand side become? -3a plus 0. All right, we can handle that. What does this imply? A is equal to 3. I happen to put them right. I always wind up with A being negative, and then I flip them around. This one came out really nicely. So what this is x squared minus x minus, oh, I got a minus in front anyway, don't I? Okay. We go back to this thing. This here, that's not good English. This here became this. The a is a 3, so it's going to be minus the integral of 3 dx over x plus 2. Okay? And then the other one was this minus is in front of both of these. Minus the integral. What's those minus signs? The whole purpose in their life is to trip you up. You know, that's the whole reason they invented minus signs, to make students make errors. Okay? And what does the other one become? B was a minus 1, so this is just a dx over x minus 1. Okay. All right. So it's the x squared minus x, don't forget that, minus, what does this become?
Is it 3 natural log of
3 times the natural log of
absolute value
absolute value
plus 2.
x plus 2
So that's a plus
plus
natural log of
natural log of
absolute value x minus 1.
x minus 1. Okay. Now,
Plus C too.
plus c. Okay. Now you can fiddle with those if you want to. It's not necessary, but you could. Just this sort of reinforces our rule properties of logarithm. X squared minus x, and let's do this one first. Plus the log of x minus 1 over, if you move this up here, that would then be an x plus 2 cubed. Okay. Plus. Now, there's nothing special about that answer, but it's just, this is the numerator part. This would be to the minus 3, so that goes downstairs here. Might be a little better to put that in bracket. I don't know. Nothing any more special about that, but okay. Now, if you look at this carefully, you'll see x certainly can't be a minus 2. Well, guess what? It couldn't in your original problem. Remember, that factored to be, okay? Nor can it be a plus 1, because you can't take the log of 0. So our 2, when we factored, we could have written off to the side x can't equal -2, x can't equal 1, and sure enough, that still holds true here. So, yes?
When you plugged in the b as -1, why didn't that change the sign?
Let's say that one more time.
Since the b is -1, when we plug that in, up 1,
Okay, where did I use -1?
above that, right above that. There.
Right.
Because
Okay. It did change the sign of this because here this was a plus b, and b was a minus 1, so I made that a minus out here. Yeah. They're just there to trick you. That's the whole purpose of minus signs, okay? And it almost did, but yeah, we managed to escape it this time. Yes?
In the earlier drawing, where the x squared minus x at the very top come from?
Yeah, where did that come from?
Yeah.
Okay. We were assuming this was our integration. When we did our division, then the integration would have been integrating this. Okay? And when you integrate this, you get the x squared. Integrate that, you get the minus x. And then the rest of the stuff we're dealing with just the partial fraction. Okay. Good question. Excellent question. Any others? Y'all are on top of it today. Any others? Okay. This wasn't in the book, by the way, so we can't check it. Now, let's go on to the next slide, which we've already done example 3. I'm not sure that I showed this last time, did I? I think we just did it on the board and I forgot to show it. For people who watched example 3 last time, it is worked by the book. I don't remember if we did this or not. Okay? I just don't remember if we did it. I don't even remember this problem. Okay? Oh, yeah, I do. Okay. We had 2 equations, 2 unknowns, and we solved those, didn't we? Remember that? Okay. They didn't show how you solved them, but let's, ooh, all that red writing here. Red writing hood. Okay. Still hurts my shoulder. I thought that I would like whiteboards better than blackboards when they first came out because of all the chalk dust and breathing all that stuff. Then I found out these markers last microseconds and you have to just keep buying them, and they're so much more expensive than chalk and I'm cheap. And they don't erase well, especially if you leave them up there too long. So I'm not all that big. But projecting on a whiteboard is way better than projecting on a blackboard, so I'm in favor of it. All right. We didn't solve this. They just said this yields this. How do we go about solving this? There's 2 ways. I can't remember. Did we do this? It seems like we did. One way would subtract this equation from that equation. In other words, change signs, make that a plus, a minus, and a minus. Okay? And that will eliminate the D, and that would give you 3C is equal to 6. Divide and get C equal to. Y'all do that, right? That wasn't anything new for you. Okay. Now, if C is equal to 2, then this will be minus 2 plus D is equal to 2. Add 2 to both sides, D is equal to 4. Okay. I don't remember doing this. I'm sure we must have. Or did I say, oh, we'll just leave it there and you finish it up? But anyway. We did, okay. The old gray cells ain't what they used to be. I don't remember. It was only 2 days ago. What? How can you remember that far? So therefore, when we split that one up, this is what it produced. But I don't remember showing the slide here, did I? I don't recall. Okay. And that's what our answer was. I kind of remember it. Okay. And don't you love it how they just go from this to that without showing you how they did it? Now this one's pretty easy. Yeah, I can follow that. And this one's pretty easy. I can follow that. This one, I think Patrick was doing that in his head, so that's okay. But this one, I think we actually worked through that, didn't we? Yeah. So that was the 2 tangent x and so on. So anyway, that's why it came out being an arctangent. Okay. Here now are the guidelines. This is where I was trying to get to. Here are some guidelines for solving the basic equation that is obtained in a partial fraction decomposition, or something like that. Okay. Guidelines for solving the basic equation. Now that's the thing that's inside the radical. Okay, no. That's after you divide it if you needed to. When you get it as an improper rational expression, and you get there with your linear factors, substitute the roots of the distinct linear factors into the basic equation. Yeah. Okay, remember, if you came up with linear factors, x plus 2, x minus 1, then the root for the x plus 2 was x equal negative 2, and the x plus 1 or x minus 1 was x equal 1. That's exactly what we did. Substitute them in and figure out what your a and b is. For repeated linear factors, that would be like if you had x plus 2 to the 5th power. Okay? Use the coefficients determined in the first guideline to rewrite the basic equation, then substitute other convenient values for x, solve for remaining coefficients. We didn't do any quite that big, but that is doable. This wording doesn't really make it pop out in my mind what you do. You basically do the same thing we did before, matching up powers. Okay. Quadratic factors. Expand the basic equation, okay, just like we did before. Collect terms according to powers of x. That's what we did. Equate the coefficients on the left-hand side with those powers to those on the right-hand side that have the A's, B's, C's, D's, E's, F's, or whatever you got in there with those, and solve for your A, B, C, and so on. And then solve the system of linear equations. We didn't need to go this far on the last one because it all worked out without solving a system of equations. But that 3, we did have to. Whatever it was, minus C plus B is equal to something. Yeah. That was solving a system of linear equations. Now, if you have a whole bunch of them, that's a good place for a matrix. But you probably, any of you know how to do matrices? Kinda, yeah. It's there. It's been a while, and unless you practice them, they're not entirely obvious. But once you do them, it's a lot like doing the equation we just did. Okay, when you had a system of 2 by 2. All right. That's the last slide. Homework exercises here include any of the odds 3 through 19. They're all at Calc Chat. 7's at Calc View. Either 21 or 23, they're both at Calc Chat. 21's at Calc View. Any of the odds 25 to 31, they're all at Calc Chat. 31 is sort of interesting because it has a square root in it. Okay? And by the way, I didn't do the thing on your book underneath the guidelines that we just had there. For further information, maybe we did do that. They have a reference there, and you're certainly welcome to look at that, and that could lead you to a paper topic, perhaps. Okay, the book can't be your source, but a reference you get from the book could be your source. Okay, but the reason I mentioned something down there is finally partial fractions can be used with some quotients involving transcendental functions like sines, cosines, and stuff. But what you do there is do your u substitution and then do your partial fraction with the u's and then go back and plug in. So that's just sort of reverse. That's what made me think when I saw 25 has sines and cosines, some squared, some not. 27 had secants and tangents, some squared, some not. 29 had exponentials, okay, and 31 had square root functions. So do a u substitution first, then see if you can do partial fractions with your u's. All right, if you need any of those done, we can do them, okay? Then do either 33 or 35. They're both at Calc Chat. You can explore doing 37 or 39. They should be at CalcChat. You can do either 41 or 43. They should be at CalcChat. And then any of the odds, 45, say, through 51, they should all be at CalcChat. I would say do the ones that are closest to what you might expect to do in your future. If you're going into modeling data, which math majors could do, or volume and centroids, which could be something an engineer might do. Epidemic models, that would be something that a biostat person might do. So it depends on which way you think you may be heading. Pick those and do the ones. Now, 8.6. Hopefully this one will open and we can do it our regular way. I've got to remember to go back and see if I can reload 8.5 because it didn't always do that. All right, things are looking better, folks. We'll go from current slide. And 8.6, or chapter 8 is still integration techniques and improper integrals. And guess what, folks? Even though you know U substitution, even though you know how to do integration by parts, even though you know how to integrate trigonometric functions, or trigonometric substitutions, or partial fractions, you know what, most of the time, if you ever do run into integration, none of the methods work. Occasionally you get one that does work. Yes, I know how to do this one. But a lot of times, nothing will work. And then you do numerical integration. Now we're going to go over a couple of different ways to do numerical integration just to sort of get you used to the process of it. These are not the neatest, cleanest, most efficient ways. There are other ways to do it. And in future courses, you'll probably hit those if you need them. But we'll show you a couple here of numerical integration. We'll approximate a definite integral using the trapezoid rule. We'll approximate a definite integral using Simpson's rule. And we'll analyze the approximate errors in both the trapezoid and Simpson's rule. Now they left out one that they're going to bring in on the backside, and that's the midpoint rule. That's a little bit better than trapezoid, but not as good as Simpson's. Simpson's is pretty good. Okay, so let's start with the trapezoid rule. Some elementary functions simply, like I was saying, do not have an antiderivative. Okay? You can't do any. No matter, there are elementary functions also. Okay, some elementary functions do not have antiderivatives that are also elementary functions. For instance, this one, there's no elementary function that has any of the following functions as its derivative. The cube root of x times the square root of 1 minus x. Hang it up, Jack. That's so messy, I don't even know what to talk about. No, okay. Square root of x times cosine x. Then try it. You won't find that as the derivative of anything. Cosine x over x. The square root of 1 minus x cubed. Yep. No substitution in the world is going to make that something easy to do. Sine of x squared, oh no. Okay? If you need to evaluate a definite integral involving a function whose antiderivative cannot be found, then write the fundamental theorem of calculus. Then while the fundamental theorem of calculus is still true, it cannot be easily applied. Okay? In this case, it's easier to resort to approximation techniques, which is what we call numerical integration. Okay? In general. Okay. One way to approximate a definite integral is to use n trapezoids, as shown here. This goes back to our good old Riemann sum type thing. In the development of this method, assume the f is continuous, that's important, and positive on the integral a to b. Yeah, unfortunately, you've got to assume that as well. May not be quite realistic for your problem, but A lot of times it is. I mean, if you think about it in business or in medicine and stuff, you very seldom deal with negative cases, right? You know, if it's negative, it didn't exist. Okay, so here's this integral, a to b, some f of x. That looks like that could be a nice polynomial function. Let's assume it's not, okay? And that represents the area of the region bounded by the graph of f and the x-axis, meaning f has to be positive, from x equal a to x equal b. So here's x equal a here, x equal b here. Now they've drawn 4 trapezoids. They let x0 be a, x1, 2, 3, and x4 be b. Okay. Now, just sort of like we did before when we did our rectangles, these are now trapezoids, which should be better than rectangles, remember? Okay, because here you're letting x, you know what the f is. You can calculate what f. You can't integrate it, but you know what it is, okay? It's an elementary function, you know. You can evaluate its value, okay? You can evaluate the value, remember those that were on the screen before? X cubed root of it, yeah. You can put numbers in and get answers for it, okay? Now, some of those are approximate numbers because they're irrational, but that's another issue, okay? You can evaluate the f function here at x equal a and at x equal x1. Okay, time out, let's back up. Let's say we took this b minus a, that's the length of this, divided it by 4, and that gives you how thick, how wide each of those are. So this one will be a plus b minus a over 4. And this will be a plus b minus a over 2. This will be a plus b minus a over 3, and this is b. Okay. All right. Now, the area of this trapezoid would then be this length plus that length times this divided by 2. Remember that? If not, picture this. Hey, it's away. I'm so happy. That made my day. Okay. So, let's get my pen back. All right. Remember, if we just flip this over on its head, that's a really ugly rendition of it. Maybe it needs to be a little taller. Okay. Let me see if I can erase some of that and not erase it all. Let's see. Well, I erased too much, but okay. That's a fair approximation. Not good, but fair. What I've done is taken this trapezoid here, flipped it this way so the long side is here and the short side is there, right? Now I've made a rectangle. The rectangle is this length plus the short side plus the long side times the width, right? Well, the width we know. That's your b minus a over 4, okay? That is the width of that. So we can add these two together, multiply it by the width, and then divide by 2, and that would give you half of that rectangle is that trapezoid, right? So you just flip it across. You do the same thing here, and you don't have to evaluate this, you already did. Just evaluate this, and now flip that one up, take half of it, and then here, and then there. Do it to all 4 of those trapezoids. Now, see this one, our approximation is going to overshoot a little, this is going to undershoot, this is going to undershoot. Our approximation overshoots, undershoots, and a little bit undershoots. So it's not going to be exact, but it's not going to be too bad. How do you make it better? Make your dx's even smaller. Exactly. Okay? Now, we're not getting down to a delta x, not that small. We're going to always have it some finite distance there, not infinitesimal, but some finite distance. And at some point, though, you get your approximation. So if you had this one, the trapezoid fits even better, and that one fits better. This one fits better. That one fits better. This one fits better. That one fits better. They all fit better, and you keep doing it until two successive decreasing of this, you get within the precision that you can measure anyway. So that's good enough, okay? Or the precision you're seeking. So that's what we do. Well, that's the trapezoid method. We're going to develop a way, I basically just described it, for approximating the areas under those rectangles, or trapezoids, okay? First, partition the interval A to B into n subintervals, each of width delta x is equal to b minus a divided by n, right? The length divided by the number of times you divide that, you know, how many rectangles you have, trapezoids you have, that would be your delta x. So this is your delta x, b minus a divided by n, okay? And then your a will be the first one, and this one will be 1 delta x added to this, added to your a. This will be 2 delta x's added to your a, or 1 delta x added to that. And however you want to do it, finally you get the last one, and that's just going to be your b, because you would be multiplying n delta x's. N delta x's. The n goes out, and to a plus b minus a is b. So yeah, that's the last. Then form the trapezoid by each subinterval, okay? And here's the figure they're referring to. The area of that trapezoid will be the function value here plus the function value there, multiplied by your delta x, your b minus a over n, and then take half of it, okay? So it's that one plus this one divided by 2, and half of that, and then times your b minus a over n. Okay. Now that looks a little messy, but really it's not too bad. You do this one time and it's done. You know what your b is, you know what your a is, you know how many intervals you got. Do it once and it's done. So you don't carry that around, you just have that. And then each of these, you're going to just evaluate here, 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 here. Evaluate each of those. Use this one once, this one twice. Once on this one, once on them. It's the right hand edge of this one and the left hand edge of the next one. Okay? So you use each of those twice, except that last one, that B, you only use that one. Okay? But anyway, that's what you proceed with. This implies that the sum of the areas of the n trapezoids, now n is not going to infinity. N is some finite number. Those n trapezoids is, that was a common factor on all of them. You've already figured out what it is. You don't even have to write b minus a over n. Calculate it, you got it down there, okay? And then you have, this was the first, with that as your width, this is your average height, you might say. Plus you do that for every one. Noticing that you have 2f of x1, 2f of x2, 2f of x, everything up to f of x minus n, f of x n minus 1, and only one of these, or 1/2 of those. But you see, because you got 2 of them, then you lose your denominator. Because 2 of these divided by 2 is just that. So it's this one over 2, plus that one, plus this one over 2, plus that one over 2. That's what it winds up being. That's what we see here. Oh, what they did to pull out the, okay, this is another way to do it. Okay. Pull out the 2's here, and then you have 1 of these, 2 of those, 2 of those, 2 of those, 1 of those. That's what they've done down here. I kind of like just using the original, not half of that, but the original of that, and doing half of this one, half of that, and then 1 of each of those. But whichever way you do it, works the same way. All right. By the way, this can be programmed. That's really nice, okay? All these calculations can be done that way. So letting delta x equal b minus a over n, you can take the limit, oh, now they're going to do it, as n approaches infinity. I kept saying that's a finite number, they're letting it go to infinity. And you do this, and that gives you what you had to begin with. That's what we're trying to do, is do the integral of this thing that you can't take an antiderivative. So why did they take you all the way around here to get you back here? I'm not sure, okay? But they did, and it's okay. It just shows that, indeed, the trapezoid rule does give you what you're looking for as n goes to infinity. But, of course, if you can't do it, then that doesn't make any sense anyway. You're going to need a finite number of n's. Your n needs to be finite. So here's your trapezoid rule. As long as x is a continuous function on AB, it doesn't have to be differentiable. It probably is differentiable, but it certainly doesn't have to be integrable, okay? On A to B, then the trapezoid rule for approximating this thing, that's what it's all about, is approximately equal to, and they put the b minus a over 2n, which is fine, times the sum of f of x0 plus 2 times this and 2 times that, and 2 times everyone else except that. And you use one of those. Moreover, as n approaches infinity, that approaches this. You can't do this anyway, so why let it approach infinity? N is some finite number. Okay. That's what numerical integration is. So here's example 1. Hey, we know this one. We can check our answer on this one. Let's see what happens. Compare the results when n is equal to 4 and n is equal to 8. We know this anyway. What would that be? Integral of sine. Missing that little thing that you feel. Negative cosine, right? Derivative of sine is cosine. Integral of cosine. Antiderivative of sine is negative cosine. So you got negative cosine evaluated at pi is, what is cosine of pi? Negative 1. Okay, remember it starts at 1, goes to 0 at pi halves, negative 1 at pi. So it's minus 1 minus a minus, because you have negative cosine, so that's plus a cosine of 0, which is
Awesome.
1. So 1 plus 1 is 2. So this should be, that integral right there is 2. Okay? Now, is that just a happenstance, or is that useful or anything? My younger brother was a professional engineer, electrical engineer, and he worked for a power company, and they were estimating, electricity is estimated with sine curves. Said they use this all the time. That one log of the sine is 2. The area under that is 2. Okay. Always is. Okay. So we're going to see how these answers compare with the number 2. Now, just looking at it, I can tell you this trapezoid undershoots a little, that undershoots more, that undershoots about the same as this one, that undershoots a little. You're going to be a little on the low side. And even when you go up to 8, you're still underneath. Okay, so you're still, neither one of these will quite reach 2. So what you do is, for n equal 4, b minus a will be pi divided by 4, so that's your delta x is pi fourths. So this will be 0, pi fourths, pi has 3/4 pi and pi. When you do pi minus 0 is pi divided by 8, that would be pi fourths, 3 pi, pi has the other. That would be that each one of these is pi 8. So each one of these intervals is pi fourths. So your b minus a over n would be pi fourths here, pi 8ths there. Over 2n would be pi 8ths here, pi 16ths there. So just depends on which way you work it. So let's do it, okay? That shouldn't be too hard to do, should it? This should be approximately. It's not going to be exact. You know it's not exact. This will be, for the first one, you want to use the b minus a over 2n? That's what the book uses. Or you want to use n. Just have to adjust your thinking on it. Which you want? I really don't care too much. You don't even know what I'm asking you. Huh? The first one, okay. Good and safe answer, right? So that would be pi eighths. Because b minus a over 4 would be pi fourths, and take half of that and you get pi eighths. Then what you put here is, the first one's easy, f of 0, well, we know what f is, it's sine, so let's just put that. Sine of 0 plus 2 times the sine of pi fourths plus 2 times the sine of pi halves plus 2 times the sine of 3/4 pi plus sine of pi. Okay, sorry I ran out of room. So that would be pi eighths. What's sine of 0? 0. That was easy. What's sine of pi fourths? Root 2 over 2, and you got 2 times that. That would just be a root 2. What's sine of pi halves? 1, and you got 2 of them, so you got 2. Another root 2, because 3/4 pi is the same, right? And then 0. Okay, so what do we get? Pi eighths times 2 root 2 plus 2. Well, let's factor out a 2 and make that a pi fourths times root 2 plus 1. I know what that is. This is root 2 is 1.414, so this is 2.414 approximately times pi fourths. But you can do it on your calculator. You don't have to do what I did. Someone punch that in and see what you get. Pi fourths times quantity root 2 plus 1. Don't use my 2.414. Second? 1.896. Yeah, that's not too bad, is it? It undershoots it. We know the answer is 2. It undershoots it just a little bit. Okay? The next one's not going to be quite so nice because I don't know these values. So 1.896, I'm going to put that here. 1.896. Okay. I'm going to erase what else we did here. Okay. This time we're going to use our interval of pi eighths. That's b minus a pi divided by 8. Okay? But because y'all want to do it the first way, that would be pi 16ths times, okay? And guess what? Sine of 0 is still 0. Okay, so don't have to write that one down. It would be 2 times the sine of pi eighths, and I don't know that one, so y'all going to have to do this on your calculator, plus 2 times the sine of pi fourths. I do know that one, plus 2 times the sine of 3/8 pi. I don't know that one, so y'all are going to have to plug that one in, plus 2 times the sine of pi halves. I know that one, so you don't have to worry about that one, plus 2 times the sine of 5/8 pi plus 2 times the sine of 3/4 pi, which we know, not just me, plus 2 times the sine of pi, of 7/8 pi. And then we all know that sine of pi is 0. Okay. Now, done this way, it's actually a little easier. You only have to enter it once. Okay. Because you know the sine of this is the same as the sine of that. Okay. So, just do 4 times, okay. However you want to do this. You want to do it with big brackets or whatever, you can do it. You could start out with pi over 16 times, open parentheses, 4 times sine of pi 8 plus 2 root 2. This would be a root 2, that would be a root 2. Plus 4 times the sine of 3/8 pi plus 2. Close your parentheses, see what you get. Did you follow that? Pi divided by 16 is out front, times, open parentheses, 4 times the sine of pi over 8. Get that one done. You know the next one. This is root 2 over 2 times 2 is root 2. Double that, you get 2 root 2. 2 times root 2. Plus 4 times sine of 3/8 pi. You have to figure out what 3/8 pi is. Same as 5/8 pi, so you don't have to do it twice. Just do it once. And then plus 2. Because sine of pi half is 1. You just got this is 1, so plus 2. Close parentheses. Anyone get it yet? There.
What do you want first?
Okay. Okay, what you mean?
Like, what's the first thing you want? You want the 4 sine?
The what?
You want 4 sine of pi over 8 first?
Oh, okay. I was just asking you to just do it on your calculator as we go.
Okay.
But we could do that. You want to do that? All right. Let's do it this way. Pi over 16 times 4 times what's sine of pi 8. Is that what you wanted? Or you want to do 4 times that? I don't care.
That's 0.0068.
You'll have to say that a little louder and slower.
0.0068.
0068? Wow. Are you in radian mode?
No.
I thought not. Okay. That sounded like a degree to me. 0. Point what? 0.02?
0.38.
Oh, it was 0.38. I didn't want to write on all these numbers. I wanted you to do them, okay? And we know what this one is. 2 root 2, was it? Yeah. 2 root 2, that's those two. Plus 4 times sine of 3/8 pi. And what's sine of 3/8 pi?
.924.
924? You are in degree mode, I mean radian mode now. Good, okay. All right. Plus 2. All right. If you want to do it that way, you can. I was more interested in you just doing all the things. I didn't have to write down anything else to get the answer. Oh, and maybe we could make this simpler by making this an 8 and make that a 2 and a 2 and a 1. Now that you've already started punching, but
I got 1.975.
1.975, is that what you said? Hey, look at that. We did get better. Not quite up to 2 yet, but we could get better. Okay? Now, without really meaning to, I really did show you a little bit easier way of doing this. And this is how you would want to program it. If you said, oh, that's not close enough. Oh, that's not quite close enough. But you already got this answer done. Then what you do is you have to adjust your number out here, but you just see you've already done these calculations. You know, all those. Then do one for here, 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 and let the put that in the appropriate number of times and stuff, and you'll come up with a better one. At some point, you're going to get so close to 2 you can't tell you're not at 2. But it depends on how many digits you have on your calculator. I wouldn't go that far. That's getting awfully close to good enough for me. Okay. And sure enough, you don't see many gaps here, do you? There are slight gaps, but it's not many. Okay. Let's see how the book did on that. They got 1.896, good for them, and 1.974, they said, not 975. I don't know how they made their error, but they did. Okay. I'm sure y'all were right. And you see, they did, oh, look at that. They copied me, didn't they? Did the same thing I did. Okay. And we had already known what we got. They say that most graphing utilities have a numerical integration feature that can be used to approximate blah, blah, blah. Since I don't have a graphing utility, I'll let you work on that. But let's look at, I hate to do this because this is almost wasting time, but if you got a book, how do you think it's going to do on a problem like this? The integral from -1 to 2 of 1 over x dx. You think you're going to get a good answer? There's a couple of reasons you should be screaming, no! Can you think of any of those reasons you should be screaming at the top of your lungs? No, you can't do that.
There's negative to 0 power.
Say again?
It would be to 0 power.
Okay. That's what you're saying is somewhere in there you got a 0, and your integrand is 1 over x, and you can't do that. Is that what you're saying? Say yes. Okay. Yeah, you can't do it for that reason. Now you said something about, what did you say?
The -1.
-1. Okay, we can look at that integral. What is that integral? If you didn't have the limits on it, what would that integral be? Integral of 1 over x dx. Please tell me you know that. Natural log of x. And you can do natural log of 2 minus. Oh, you can't do the natural log of -1. So there's another reason you should be screaming. No, this is not going to give you a right answer. Even no matter what kind of technology you got, it's either going to give you a totally bogus answer. The trouble is, this integral is not integrable. Okay, not with those limits, because you're integrating past 0. And if you picture what that graph looks like, here's what the graph of 1 over x looks like. And you're going from, what, -1 to 2. Now, how in the world are you doing that? You're not. All it's going to give you, if it gives you anything, will give you this value right here. Because this is negative, that's positive, and there, you can't do them anyway because they cross 0 there. But if you could do them, they'd cancel each other out, and you'd only get that part. So don't expect your graphing utilities to give you answers for problems that make no sense to begin with, which this one doesn't. All right, have we run out of time? awfully close. Sorry about that. I took too much time. Oh, let's see how they did it. When n is equal to 4, here was that was approximately equal to pi 8, which is that's pi fourths over 2, sine of 0, 2 sine pi fourth, blah, blah, blah. We did exactly that. That came up to pi 8 times 0 plus root 2 plus 2 plus root 2 plus 0, which is pi fourths over 1 plus root 2, which is exactly what we did and got 1.896. When you did it for pi 8, the delta x was pi 8, you pull a pi 16th out, half of that, and you still got your sine 0 and your sine pi, which is not going to contribute anything. Now you got your 2 times sine pi 8, 2 times sine pi 4, blah, blah, blah. And that gives you, because these two are the same, those two are the same, and those two are the same, you get, and then your sine 2 times sine of pi is 2. That's where you get those numbers. And that gives you 1.974 they said. So they may have made a mistake, rounded poorly or something. Okay, for that particular integral, you could have found the antiderivative. Yeah, we knew that. We had already done it. All right, that was what they do with trapezoid rule. Give you a pretty short thing of it, but at the top of page 561, they introduced the midpoint rule. Like I said, they just going to mention it. We'll mention it also, okay, and come back to that. We'll start there next time and then move on to substance rule, okay? Homework exercises. You can do any of the odds, 3 through 13. They're all at Calc Chat. 3's at Calc View. You can do, well, let's just stop there. Oh, no, both of them say. So just do the trapezoid rule part, then later we'll do the Simpsons rule part. Okay. So 3 through 13, only the trapezoid rule. Later we'll do Simpsons. All right, good deal. Any questions? The trouble is these can take time. That's why you use computers to do them.